Okay, so at this point we talked about sort of the really simple version of a buffer problem, which is how you can use the Henderson-Hasselbalch equation to compute what the ratio of the weak acid and conjugate base are at the pH needed to prepare the buffer. And that assumes that you have physical reagents of both of those things, the weak acid and its conjugate base. But more often than not, in an actual laboratory, you only have one of those things, like the example here. And this is a really practical example. It's a little bit more involved, but much more likely to be encountered in a real chemistry scenario. And so the example is that you want to make a buffer that's 0.1 molar. That's the total buffer concentration. And you want to make it at a pH of 5.1 with a volume of 100 mils. And you have HF, that's your weak acid. That means you want to make a buffer of HF and F minus, fluoride minus. You don't have fluoride minus in the lab, but you do have strong base. And so the idea here is that you could add this strong base, which is essentially hydroxide ions, to remove some amount of the protons such that you have some fluoride in the system and HF. Right? You don't want to add so much KOH that you completely neutralize this. You want to add just enough that you neutralize just enough so that the ratio of HF to F is exactly what you would predict based on a Henderson-Hasselbalch equation. So let's walk through this step by step. And the goal here would be to figure out what mass, in this case, of this solid and what volume of this stuff do we need to mix together with water at 100 mils to make this system work. So there's a lot going on here, but it has all the mechanics that you already know how to do. We just need to make sure we understand the sequence of logic. So as always, for any of these multi-component problems, the best tactic is to just figure out what you know and what you don't know. So what we do know from this problem is that we're trying to make a buffer at a pH of 5.1. So the pH is 5.1. We know that the total buffer concentration is 0.1 molar. And we also know from our prior knowledge that when we talk about buffer concentration, like it's described in this problem, what we really mean is the two components of that buffer add up to that total concentration. And we know from the way that this is written that we have HF and we have its conjugate base, but we need to prepare that base. We don't have it, we don't have a bottle of it. But those two things should add up to 0.1. We know the final volume of the system should be 100 mils. And we have this initial concentration of HF, the weak acid, at 0.8. So we have a bottle of that. And we have a solid chunk of KOH that we can weigh out and add. What do we not? So the first thing we don't know, but we could probably find is, well, what is the pKa or the Ka of the system we're using, HF? Of course, that's a constant. So we just need to find that because, of course, we're going to need it. And really the question that we're being asked here is what mass of the strong base and what volume of the weak acid, since this is a solution, an aqueous solution, do we need to make the solution under all these conditions? So one of these things we can find immediately just by looking it up. The other two we're going to have to extract via the problem itself. So a quick Google search for pKa of HF or look in your book gives us a value of 3.17. So I'm moving that up to the known category, which means I can get rid of this as an unknown and really start to focus in on what is going on in our system. Okay, so the first step here is to just start with the acid-base equation that's operative in the system. And so we had already identified that we're dealing with HF as the weak acid and fluoride, conjugate base, and we know the pKa, so we just write that up because clearly that's going to be something we're going to use. Next step then is just to use the Henderson-Hasselbalch equation to figure out what the ratio of those two species is, HF to fluoride, under the constraints of the problem. So we know that the pH needs to be 5.1, so I sub that, and I know the pKa of HF is 3.17, so I can solve this to figure out what the ratio of those two things should be in order to maintain a pH of 5.1. So some quick algebra here, and I get a ratio of the conjugate base here, A minus to HA, and I'm just using these in place of HF and fluoride for simplicity, but I could just as well write those. That has a ratio of 85, so we could figure out what that means in terms of the total concentration. So in other words, our next step is to convert this ratio of 85 to 1 meaning 85 parts of the base to 1 part of the acid, we need to convert that to an actual concentration instead of a ratio. And in the previous video, I showed you 2 different ways to do that. I'm going to use the system of equations way, so I'm going to write up 2 equations and then solve for those 2 unknowns. So the 2 equations, the first one is just coming from the ratio. So this is an equation already, A minus over HA equals 85.1, but I just solved for one of those species, so now it's A minus is equal to this. And then the other one, this one's easier to forget, but remember, when we're told the total concentration, it's implied the total buffer concentration is really just the sum of the acid and its conjugate base. And so that's always an equation you can write. So now I can just substitute A minus into this and solve for HA and do the same thing for A minus. Okay, the solutions look like this. So HA is equal to 0.001161, and I know that HA plus A minus has to add up to that total buffer concentration, so I could just pop that back in here, take 0.1 minus that gives me what's left over is A minus, which is 0.09883 molar. Okay, so we're not done yet. This is true. These are all true. These are the concentrations that I need to establish a pH of 5.1 for the HF system with its conjugate base. But we need to take this a couple steps further because we don't have A minus, which in this case is fluoride, available to us in the actual practical problem. Because remember, we have HF, which means we have HA, but we only have KOH as our solid. So we have to do a couple things here. So just for clarity, I went back and replaced all the HAs with HFs and the A minuses with F minus, just so that it's really obvious here. And to clarify, the challenge in this problem, why we can't just stop, is because we don't have a bottle of F minus or sodium fluoride for that matter. We don't have any fluoride source except for the HF. But we do have OH, and we know that when we add OH to HF, it will make fluoride. And so the next step of the problem is to figure out, okay, so if this is the final concentration of HF that I need, and this is the final concentration of fluoride, how much OH do I need to add to HF to get to these final ratios? So that's just going to be some algebra, but that's the logic we need to use to finish this up. So that step then is how much KOH do we need to add to make fluoride in this concentration. But remember, the part that people forget often is that you don't get to make that from scratch, you got to make it from HF. So that means we got to add excess HF too, such that when we react it, we end up with this much left over. And so the reaction that we're running to get to these is really HF plus KOH, right? Some amount of that, such that the balance between HF and KF, or F minus in this case, those two are at the ratio that we've determined so far. So the way to do this is to actually remember how much our actual overall buffer concentration is, and actually make the HF at that concentration. Because we know this is the total concentration, we could just start with pure HF at that concentration and then just add an amount of OH or KOH until we've decreased the HF to this concentration. We will, at the same time, will then have produced the exact amount for this amount of fluoride so that the ratio is satisfied. So that means we are trying to make a solution of HF at 0.1 molar. So we need to figure out what that is. So we'll do that here in a second. And then we need to figure out how to make or how much hydroxide then to add to that solution to get this 0.09883 molar fluoride. So those are the 2 conditions which were already pre-established. Now we just need to think about them practically. So we have a solution of HF already at 0.8 molar. So that means what do we need to add to get that, and then what do we figure out for the other? So for the HF solution, that's pretty straightforward actually, because we just have a more concentrated solution of that. So we need to do a dilution. That looks like an M1V1 problem where we have our initial concentration of HF. That's the bottle we have in the lab. It's 0.8 molar. We don't know how much or what volume we want of that, so we say that's X. So there's M1 and V1. and that's equal to M2V2. So M2 is your final concentration. So we want that to be up at 0.1 molar, and we want a total volume of this whole buffer to be 100 milliliters. And so we can solve that for X. Okay, so that turns out X is 12.5 milliliters, and so that means we're going to have some volumetric flask that has a volume of 100 milliliters, and we are going to take a volumetric pipette and add 12.5 milliliters of the more concentrated HF to that vessel, and then we will be able to bring the rest of it up with water up to the total of 100 milliliters. That's the first step. So visually that looks something like this. We've got our 100 ml vol flask, and then we're going to take 12.5 mils and pipette it directly into the bottom of there, so it'll look like that. Now we need to add some amount of KOH, because remember at this point we've added enough HF that we've made the whole solution HF. It's 0.1 molar. We don't want that. We need to convert some of that. So to convert that, we just need to figure out how much hydroxide solid to get to this concentration. So this one's actually pretty simple too, because we know that KOH reacts 1-to-1 with HF, and so that means every bit of KOH that we add, it's going to fully convert that to the fluoride, which is what we want. And our target is 0.09883 moles per liter. So we could start with that. That's our goal. We want 0.09883 moles per 1 liter. We want 0.1 liters because it's 100 milliliters. That's our total volume. And we want to figure out how many moles then, or how many grams of this do we actually need to weigh out. So we need the molecular weight of KOH. So there's 56.11 grams KOH for every mole of it. And so we can go through this. You can see these units go away, the liters go away, so that we're in moles. Now the moles go away, and we're left with grams of KOH, so we can solve. That gives us 0.554 grams of KOH. Well, what does that mean? Well, it just means that's exactly how much of that strong base we need to add to our original solution of HF. And what it's going to do is it's going to convert exactly enough by this reaction of that HF such that it produces exactly 0.09883 moles of per liter of fluoride, and leaves left over then this exact amount of HF, such that the ratio of these two things is exactly 85.11, which means that the pH of the system will be 5.1. So in practice, what does that mean? Well, that just means that this next step, this bit of stuff, the 0.554 grams, you weigh that out on a balance, you add that to your flask here, so now there's a chunk of solid that's dissolving down there. They're reacting and getting warm, and then once they're done and mixed, then you fill the rest of this flask up to the dashed line with water, and that whole thing then has exactly 100 milliliters, and it has exactly the concentration fluoride and HF once those reactions occur, and you have a pH of 5.1.